this lesson, what you've learned so far is that reaction rate can be affected by, there are 3 different factors that can affect your reaction rate. The first one is temperature. Okay, so the higher your temperature is, the faster the molecules are going to be moving. So you're going to have more collisions, and they're going to be happening with more energy. So they'll have enough energy in order to overcome the activation energy. So you'll have more reactions, the reaction rate will increase. The second thing that affects your reaction rate is the concentration of reactants. So the more reactants you have, the faster your reaction rate, because you're going to have more collisions. Your last thing that affects your reaction rate is your catalyst. So what a catalyst does is it goes in and it lowers the activation energy. The higher your activation energy, the slower your reaction is going to be, the reaction rate is going to be, because you have a bigger hill that you have to get up over in order for the reaction to occur. So what wasn't discussed, though, is the fact that a reaction can actually be reversible. So if you look at this reaction here in front of you, you've got H2 plus I2 producing 2HI. Notice, for the first time ever, you have a double arrow. And what that double arrow tells you is that H2 and I2 can produce HI, but HI can also produce H2 and I2. So if you look at time equals 0, because you only start off with H2 and I2, the reaction rate is going to be pretty fast in the forward direction. But as more and more of the H2 and I2 react with one another, their concentrations are going to be decreased, which means, based on the idea with concentration, as your concentration decreases, your reaction rate decreases. So you see that in red as the arrow gets shorter and shorter. However, as you get more and more product, since that product is acting like a reactant, your reaction rate is going to get faster and faster and faster and faster until you get to the time equals 24 hours, where the rate of the forward reaction equals the rate of the reverse reaction. And at that point, you are at chemical equilibrium. You wouldn't see a change in the concentration of H2 and I2 or HI, because H2 and I2 are going to be used up at the same rate that HI is used up. So there's no change in concentration, because at chemical equilibrium, the rate of your forward reaction and the rate of your reverse reaction are the same. Now, that does not mean that at chemical equilibrium, the concentration of H2 and I2 is the same as the concentration of HI. That's not the case. All chemical equilibrium is telling you is that the rate of the forward reaction, H2 and I2 being used up, equals the rate of HI itself being used up. So the rate of the forward and the rate of the reverse reactions are the same. So we've now taken that concept of your rate of reaction and now said, hey, guess what? A reaction can actually be reversible, and when the rate of the forward and the rate of the reverse reaction are the same, you are at a point which is called chemical equilibrium.
But now we're going to put a number to it. Okay? So the value that we use to describe the state of our equilibrium is called our equilibrium constant. All right? So as always, we can express equilibrium numerically, and we're going to do that with our equilibrium constant. So if I give you a generic reaction like the one you see below, what you will do to find your equilibrium constant, and we represent that with KEQ, okay? Your KEQ, your equilibrium constant, will be equal to the concentration, those brackets mean concentration, so the concentration of C, right, which one of your products, raised to its coefficient, which is the little c, times the concentration of D raised to its coefficient, divided by your reactant. So the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. Okay, so let's look at an example. So it says, determine the value of the equilibrium constant for the reaction below. So it's N2O4 becomes 2NO2. And I give you the concentration of your reactant in your product. So all you need to do to find your KEQ is you're going to take the concentration of NO2 and you're going to square it, because the coefficient for NO2 is a 2. And then you're going to divide that by the concentration of N2O4. Okay? So all you need to do now is plug in the values. So it's going to be 0.571 squared divided by the concentration of N2O4, which is 1.5 times 10 to the negative third. And so when you find your answer, it's 220. Okay? I rounded to 2 significant figures, so it's 220. And that's your answer. Now the question becomes, Why exactly does KEQ matter? Why are we calculating that? Well, that lets us know what we have more of. Do we have more products, meaning our products favored? Or do we have more reactants? Are reactants favored? So before I go to the next slide, which breaks it down for you, if you think about it, you have products over reactants. So if you have more products than reactants, meaning your products are favored, that means your KEQ, your equilibrium constant, is going to be very large. It's going to be larger than 1. Okay? If you have more reactants than products, then that means your KEQ is going to be less than 1. It's going to be a fraction. So let's look at this. Here, if your KEQ, also called your KC, because we used concentration, if it's around 1, that means you have about equal amounts of reactants and products. Okay? If your KC is large, right, if it's much larger than 1, what that means is that your products are going to be favored, meaning that your reaction, the forward reaction, is essentially complete because the forward reaction proceeded to produce mostly products, meaning you have very little reactants left over. If your KC is very small, what that means is that you have more reactants than products, meaning your reactants are favored. So in this case, very little of the reaction actually took place because you have so much reactants when compared to products. So that's what your KC or your KEQ tells you. If it's really large, that means your reaction proceeded towards the product significantly, right? Your forward reaction did. If you have a very small KC, what that means is that very little of the reaction actually took place, meaning that your reactants are going to be favored. And if your KC or your KEQ is about 1, then that means you've got a kind of a typical reaction where your amount of reactants equals the amount of products. Now that we've talked about the quantitative value of your equilibrium constant and what that tells you about whether your products or your reactants are favored, I'm now going to show you ways in which you can manipulate equations and therefore how to manipulate your equilibrium constant. So this is the Haber process, nitrogen reacting with hydrogen to form ammonia. And the first question in A simply asks you whether products or reactants are favored. So let's review how you determine that. Well, first I have to actually calculate my equilibrium constant. So I know that my Kc, my equilibrium constant, equals my concentration of NH3 squared all over my concentration of N2 times my concentration of H2. And I'm going to cube that. Now I'm just going to plug in my values because I know all of my different concentrations. So into this, for the concentration of NH3, I have 2.1 times 10 to the negative second. I'm going to square that all over the concentration of N2, which is 8.5 times 10 to the negative first, times the concentration of H2, which is 3.1 times 10 to the negative third, and I need to take that value and I need to cube that. And so what I end up getting for my Kc is that it equals 17,415. Okay, so I'm going to round this to the correct number of sig figs. I'm going to just say 17,000 is what my Kc equals. Now, since this is much larger than 1, what that tells me is that the concentration of products, of what has been produced by products, is much greater than for the reactants, which means that my products are what are being favored in this equilibrium reaction. Right? Now let's actually see how I can manipulate this Haber cycle process, this reaction, and what I need to do in order to calculate my equilibrium constant as a result. So if you look at B, what you should notice is that this reaction right here is just the exact opposite of the reaction I had above. So my Kc for this is going to be equal to the concentration of N2, because that's now my product, times the concentration of H2. That's going to be cubed all over the concentration of NH3, and that is going to be squared. Now what you should notice this versus this. Well, how does my Kc here compare to my Kc here? Well, this Kc, to get this equal to this, all I need to do to my Kc and to this is just flip it. So my Kc, this, is actually just going to be equal to 1 over this Kc will give me this equilibrium constant. So what that tells me is if I flip a reaction, what you have to do to the equilibrium constant, you just have to find the reciprocal of it. You have to flip it as well. So if you flip a reaction, then the equilibrium constant, so the Kc, is going to be equal to just the reciprocal. Because all you have to do to get the original equilibrium constant is flip this reaction, so that's all you got to do to your Kc. Now, let's look at what happens if, notice here, all I've done is I've multiplied all of my coefficients by 2. That's the only way it's different from A. So if I find my Kc of this guy, I know that this is going to be equal to NH3. Instead of squared now, it's going to be raised to the 4th. And then this is going to be N2 squared. And then this is going to be H2 to the 6th. And so if I want to get this equilibrium expression looking like what it did in A, what I could actually do is take NH3, square it, all over just your N2 times your H2 cubed, but then take the entire expression and square it, because then I would get NH3 to the 4th, N2 squared, and H2 to the 6th. So what I'm going to end up doing to my equilibrium constant is I'm going to raise it to whatever value I multiplied my entire reaction by. So you're going to raise it to the number that multiplied reaction by. Now, I'm going to go over this again at the very end of this video, but there are just 2 ways that I can manipulate a reaction. Let's now look at another example, but in this case, I'm not just going to be flipping reactions or multiplying them by a constant. I'm actually going to be adding up reactions, just like I did with Hess's law. All right, so if you look at this example right here, it gives you the reaction. Oxygen reacts with oxygen to form ozone. And then it actually gives you just 2 different reactions with your KEQ. So this should bring up memories of Hess's law quite a bit. What I want to do is I want to sum these 2 reactions together in order to get this final reaction, which is exactly what I did with Hess's law, except now I'm dealing with my equilibrium constant. All right, well, I want oxygen with the monatomic oxygen on my right-hand side, on my reactant side. So what that tells me is that I'm actually going to want to flip this reaction above. So I'm going to flip it quickly. And so in order to flip it, remember, when you flip a reaction, the equilibrium constant, you just need to find the reciprocal of that. So I'm going to take 1, and I'm going to divide it by 6.8 times 10 to the negative 49th, and I end up getting 1.5, or 1.47, times 10 to the 48th. Okay. Now, if you look here, I want O3 on my product side, so I'm going to also have to flip this reaction. So I'm going to do NO2, reacts with oxygen, and it forms O3 and NO. All right, so since I flipped this reaction, what that tells me that I need to do is I also need to flip my equilibrium constant by finding the reciprocal of it. And so when I calculate that, what I end up getting is 1.7 times 10 to the 33rd. Okay. Now I'm going to sum these reactions together to make sure that I don't actually need to do anything else to my equilibrium constants. My nitrogen monoxides cancel out because they're on opposite sides. my nitrogen dioxides cancel out, and what I'm left with is simply oxygen reacting with O2 to make O3. So that's the reaction that I was interested in. Now, instead of just adding these two like I did in Hess's law, I added the heats of reaction. Now here, I actually need to multiply my KEQs, my equilibrium constants. So I'm going to take 1.7 times 10 to the 33rd, and I'm going to multiply that by 1.5 times 10 to the 48th. And what I end up getting for my KEQ for this equation, for this reaction, is 2.6 times 10 to the 81st. So in the examples that I just talked about, we looked at 3 different ways of manipulating your equilibrium constant. The first one that we looked at was when a reaction is reversed. So if you reverse a reaction, your equilibrium constant is going to just be the inverse of the equilibrium constant of the original reaction, just 1 over that original value. If your reaction is multiplied by a coefficient, then the equilibrium constant is just going to be raised to a power equal to that number. So in the example, I multiplied my reaction by 2, therefore I needed to raise my equilibrium constant by 2. Finally, if I have a multi-step reaction, the equilibrium constant for the net reaction made of 2 or more steps is simply going to be the product of the equilibrium constants for those individual steps. So in the example, I flipped both of the reactions, so I found the inverse of the equilibrium constant, and then to find the equilibrium constant of the reaction I was concerned with, I simply multiplied those new equilibrium constants together. So those are the ways that you can actually manipulate your reactions and subsequently calculate your equilibrium constant after you've completed those manipulations.